Hello everybody. Today we'll learn a new model MM Infinity and MMss. MM Infinity, it's first M for Poisson arrival, second M for exponential service, third infinity is infinity servers. Like MMS, independent servers, parallel service channel, identical servers, random choice of idle servers, and infinite for infinite size or buffer, infinite population, and FIFO. So it's the Q model of MM infinity is we have n server, identical server, parallel n server. So for n equal to 1, mu, n equal to 2 mu, the total service speed, till n equal to n will be n mu. So the Markov chains will be for each birth process, we have n mu, n plus 1 mu, n plus 2 mu, and so on. And so on. So service rate will equal n mu. It's a special case, of course. This is special case. So the MOPs will be P0 equal summation of n factorial rho power n from s to infinity, which is equal e power minus rho, equal e power minus rho. So Pn equal rho n over n factorial e power minus rho. Okay, this is special case. Here we have s goes to infinities, then rho over s limitations. The limit will be go to 0. Okay. The same, utilization is the same, u equal 1 minus p0. Ls, summation of n pn from 0 to infinity, which is equal to rho, lambda over mu. So Ls, the average number of customers inside the system will be rho over mu. Ws equal Ls over lambda, which is equal 1 over mu. So the waiting time, it's 1 over mu. Okay? As you can see, Ws 1 over mu, Ls equal rho means no queue system. No queue system. Any arrival gets served immediately. Okay, so LQ equal to 0 and WQ equal to 0. Okay, it's a special case, this model. Okay. Any question for this model, MM infinity? Okay. Now, MMss. Special case here. It's similar to MMsk, but here K equal number of server. So, Poisson arrival, exponential server, S server, independent servers, parallel, identical server, random choice of ideal server, and finite system size equal to S. Now K equal to S. So it's a special case of that. Infinite population, FIFO. Okay. Here, we don't have a queue. Example, MM33, when K equal S, okay, so we don't have a queue. Okay, so always we lose. Here we have lose system. This is bad system here. We have lambda b will be big. Lambda b will be very large. So no queue, only the server, no queue on this system. In the steady state distributions will be n mu if n less than or equal to s. Okay, so maximum we have s customers. Maximum we have s customers. Okay, the P0 will be equal summation from n equals 0 to s rho power n over n factorial inverse. So Pn equal rho power n factorial P0 for n from 0 to s. Also, this system known as Erlang B model, B model, okay? The MMSK is Erlang K model, okay? Had a B model. So it's a special case of MMSK. MOPs, we have similar to SK, lambda E will be the same, but PS minus 1 for lambda times 1 minus PS. Lambda E equal lambda times 1 minus PS. In effective arrival, lambda B equal lambda times PS. Always we have utilization equal 1 minus P0. Okay. L will be summation IPI equal rho times 1 minus PS. So L or LS equal rho times 1 minus PS. Rho S equal LS over lambda E, which is equal again, because we don't have a Q, again 1 over mu. No Q system. Also now LQ equals 0 and WQ equal to 0. So it's similar to infinity, except for L. LL infinity, W equal 1 over mu, LQ, WQ equal to 0. L هونيك equal rho. In MMS, L equal rho times 1 minus PS. Difference between infinity and MMSS in L. L here equal rho times 1 minus PS. In infinity, rho equal rho, L equal rho. The same for WS, LQ0, WQ0. Okay? This is special case. Okay? So it's small lecture now. Okay? Later we'll take an example. Okay? Any question? Any question? Good. I will stop recording.